I'm going to talk about Introduction to Quantum Computing. This is a course I took over the past year. I'm going to try and present the whole thing to you in 45 minutes. So the first 5 minutes or so, I'm going to go over the whole thing in 5 minutes, and then go over it again at a little deeper level in 20 minutes, and then talk about some advanced and miscellaneous topics. So the course I took was sponsored by IBM Quantum. It is actually geared toward high school students, and then they opened it up to university and workforce students. It's kind of interesting because the first semester, October through December, was basically covering all of college math, junior through senior level, which of course is pretty ambitious when you're trying to teach high school students. And then January through May was the actual quantum stuff. Now, the way to think about quantum computing is as a coprocessor, like a GPU card. You're not going to be running Microsoft Word on a quantum computer. You're just going to be offloading your complex calculations to it. Now, the mantra for quantum mechanics when it comes to quantum computing is superposition, entanglement, and interference. So superposition means a qubit can hold the values 0 and 1 simultaneously, actually to different degrees. Entanglement means if you have n qubits, you can have 2 to the n values simultaneously. And interference means it's not just amplitudes within the qubit, there are also phase angles. Now you put these all together. If you have 10 qubits, you can hold 10 24 values simultaneously, where each value is actually 2 values, an amplitude and a phase angle. And both of those, the amplitude and phase angle, are continuously varying, so they're not actually binary. So when you encounter quantum computing, you most often encounter 2 very powerful and well-known algorithms. First, Shor's algorithm for factoring large numbers, and Grover's algorithm for searching, which interestingly, these complex algorithms were developed before the first quantum computer was even built. So just to take a quick look at Shor's for factoring large numbers, it does it by using the quantum Fourier transform in the background, which is kind of interesting, right? Because factoring is all about number theory, and number theory is all about periodicity. Well, that's what the Fourier transform is about. It's about periodicity. So it somehow uses that. It's number theory beyond what I understand and beyond what I can explain. But it runs, this quantum algorithm runs in log cubed n time, compared to a classical computer that would take n log n. And so, comparing, take the log n away, and then you're comparing n to log squared. N is much bigger than log squared, and there's a possibility this may break RSA encryption in 2037 or thereabouts. Taking a quick look at Grover's algorithm, if you have q qubits, then we can search over a space of 2 to the q values, and each time you run an iteration of Grover's algorithm, it's called the Grover iteration or amplitude amplification, we increase the amplitude of the correct answer slightly, and we decrease the amplitude of the incorrect answer slightly. And it takes square root of n number of iterations for the incorrect answers to completely go away and the correct answer to be at full amplitude. Well, a classical computer just doing a linear search is big O of n, which doesn't sound that much different than square root of n. That's what, half a degree of a polynomial. But consider, if you have 1 million items you're searching for, that means it only takes 1,000 iterations. If you have a quintillion items, so-called exascale, these terms exabyte, exaflops, remember the prefixes giga, tera, peta, exa. Exascale is considered human brain level. So if you have a quintillion items to search over, it only takes 1 trillion iterations. In a classical computer, that just takes a few seconds. In terms of the hardware, so this IBM Quantum Experience, these are cloud accounts. They were free for us. Actually, they're free for anyone. It's 5 qubits on a chip. And it has to be it has to be cooled down to 0.5 Kelvin because it's a superconductor, and that's what this is. It's a dilution chamber that cools it down to 0.5 Kelvin, and then to flip qubits around with gates, basically you need to pump microwaves in. So that's what these signal generators are. They're pumping microwaves into this chip so that computations can be performed. This is the development environment. So this is the training wheels version. You drag and drop these gates onto these quantum circuits. But that gets tedious if you have a larger circuit, and then you switch over. In that case, you switch over to Jupyter Notebook, which IBM Quantum Experience has on there. You import their Qiskit library, and you build up your circuit, and then finally execute it. So this concept of building and then a circuit and then executing it, it's analogous to building up a flow in Spark Streaming or TensorFlow. All right, so now let's go over all that again in more detail. And now we have to get into some math. Try and bear with me. I'm actually going to spend quite a bit of time on this slide. So this is how we typically represent the state of a qubit. This isn't actually what a qubit looks like. It's just a convenient mathematical representation. Here we're looking at an arbitrary state of a qubit called psi, and here it is psi. It's some superposition of the 0 state and the 1 state using coefficients alpha and beta, where alpha and beta are actually complex numbers. Now, looking at these two complex numbers, you would think that we would need some four-dimensional way to represent this because we have four numbers here, A, B, C, and D. But it turns out we only need 2 dimensions. And we're able to get rid of 2 other dimensions through some constraints that we're bound by. The first constraint is that alpha squared plus beta squared has to equal 1, and that's because alpha and beta are actually related to the probabilities. So if this is psi, the probability that we're going to measure a 0 is alpha squared, and the probability that we're going to measure a 1 is beta squared, or the magnitude of beta squared, since beta is complex. And once you measure a qubit, the psi, this psi position, this exact position, it goes away, it disappears. It's going to clamp to either 0 or 1 once you measure it, and then every time you measure it after that, it's just going to be 0 or 1. That's just the nature of a qubit. You can maintain an arbitrary psi position as long as you're not measuring it, but once you measure it, it's going to be either 0 or 1. Now, these names, 0 and 1, are actually, to me, a little bit suspect, right? Because look at the way they're defined in terms of vectors. 0 is defined, or 1, 0, I should say, is defined to be 0, and 0, 1 is defined to be 1. And anybody who's done linear algebra or any abstract algebra, this doesn't look like a 0 component at all, right? And so actually some people represent the 0 as an up arrow, meaning spin up, and some represent the 1 as a spin down, as a downward pointing arrow. Okay, so this is one constraint. We start with 4 dimensions. This gets rid of 1 dimension that the probabilities have to sum to 1. The other thing to notice, okay, so this is just a regular complex plane, and so we have an A plus BI for alpha, and we have an A plus BI here, and there's a phase angle here, even though it doesn't have a Greek letter. So there's a phase angle for alpha, and there's a phase angle for beta. But it turns out we only really need the difference between the phase angles, and that's called the relative phase. Now, why do we only care about the relative phase and not the absolute phase? Well, we can draw some analogies to other parts of physics. So go back to physics 1 and remember the ball rolling down the ramp. You have potential energy. You have the potential energy at the top of the ramp and the potential energy at the bottom. You don't really care about the difference. You don't care about measuring absolute gravity of the Earth and so forth. And the same thing with electrical charges. There's only electricity if there's a difference in potential, right, between the 2 terminals. So that gets rid of another dimension, and so that means we can represent a qubit state using only theta and phi, those 2 dimensions. Those are the only 2 dimensions we need, and this is the alternative representation. So theta is basically represents whether you're going to be measuring a 0 or 1 or the probability thereof. And phi is a phase angle, which is another, the phase angle is like another place you can shove information in a qubit, but there's no way to directly measure the phase because you're only going to be able to measure basically, essentially, theta. This is an alternative visualization of a qubit state, basically of the probability of 0 being represented as the percentage covered by this blue, and then these little lines here are the phase angles. Oh, I forgot to mention something over here. So this is so 0 and 1 are obviously special qubit states. There are semi-special qubit states, plus and minus. So these are 50-50 superposition states. So here the alpha is 1 over the square root of 2. And so alpha squared is 1/2. And so for this, the probability of measuring the 0 state is 1/2. And same over here, probability of measuring 1. The 1 state is 1/2. And also over here, this minus state over on the back side of the sphere, beta is negative 1 over square root of 2. Beta squared is 1/2, so it's also 50-50 back over here. And this is the alternative representation over here. This is the plus state, and then this is the minus state. The circles are the same size, 50-50. It's just that you have a little bit of a different phase angle down over here. All right, so now let's talk about applying gates to those qubit states. So the first gate we're going to talk about is the X gate. This is a rotation about the x-axis. So let's say we're starting out in the 0 state and we apply the X gate to it. What we do is we put our thumb and forefinger on this x-axis and we turn down the volume on our car stereo, and that's going to rotate this by pi radians down to the 1 state. So the X gate is sometimes called a bit flip state, but more accurately it's a rotation by pi radians. Similarly on the Y gate, it's a rotation about the Y axis. If we start out in the 0 state, put our hand on here and roll the typewriter platen backwards, it's going to rotate through here and end up in the 1 state. So we end up at the same place, but through a different path. The H gate is half the rotation of the Y gate. It's still rotating about the Y axis, and this is actually a very important gate because this is what allows us to get into superposition. So if we start off with the 0 state and we apply the H gate to that, put our hand on the typewriter pattern, and then rotate it by pi over 2, and we end up over here at the plus state, that 50-50 position, superposition. Now, let's say that we applied the H gate, and then on top of that, right after that, we apply the Z gate. So it's going to be a rotation about the Z axis. We put our thumb and forefinger up here on the Z axis, open our water bottle, and it goes back over here to the minus state. Now, to show how to apply these matrices, so let's say we have this very simple quantum circuit here. We start off with an input of the 0 state, and then we apply an X gate. Remember, that's going to bring us down here, and then actually through this way back to 1, and then the H gate is going to go through this dimension over to the minus state, and that's why we end up at the minus state. Now, in terms of matrices, we write the circuit, left to right, but when we do math and functions and matrices, we write stuff right to left. So that's why, the 0 state, 1, 0 is over here on the right, and then this is the X gate over here, and then this is the H gate over here. Well, you multiply this out, you end up with 1 over square root of 2 times the vector 1 minus 1. Well, you can break this out into the 0 and 1 state into a linear combination, and that's because, for the linear algebra inclined, you'll notice that 1, 0 and 0, 1 form a basis, so you can always do this decomposition, and, well, this is just the minus state. All right, so there's some rules that we have to live by. And the most onerous rule is the no cloning theorem. If a qubit has a value, you can't like make a copy of that value. Well, you can make a copy, but then you have to destroy the first one. So that's what that means. And then when the qubit can have arbitrary continuous values for both its amplitude and its phase. But when you go to measure it, you can only measure the amplitude, and then it clamps to either 0 or 1. No continuous values. And because measuring is so destructive, that means you have to be very careful not to do any measurement until the very end, because otherwise you're going to destroy your internal state. And similarly, noise counts as a measurement. Like if your 0.5 Kelvin dilution chamber goes up to 1 Kelvin, that's noise. Or if somebody turns on the microwave in the office, that's noise. All right, multiple qubits. Well, you can have multiple qubits kind of running in parallel. That's not really very interesting. What we want to do is we want to entangle the qubits so we can get our exponential number of values. This is the most basic way to entangle qubits. You use that H gate, the Hadamard gate, followed by what's called a CNOT gate, which is the most fundamental 2-qubit gate. It's actually is really like an exclusive OR. This top line is called the control line. The bottom line is called the data line. If the control line is 0, nothing happens to the data line. If the control line is 1, it applies the X gate, essentially. And that's why they have a little cross here, meaning X. It does a bit flip. So now that we're into 2 qubits, we no longer have our little 2x2 matrices. Now they're 4x4 matrices. And then when we get down to a 3-qubit gate, this is a controlled NOT, which means both of these top 2 lines have to be 1 for the bit flip action to happen on the data line. Now we need an 8x8 matrix. Again, this is when we have 3 qubits, it's not 3 values, it's 2 to the third values, 8. And so that's why we need an 8x8 matrix to represent that. All right, let's take a little deeper look at those 2 algorithms again. Okay, so Shor's algorithm for factorization, again, that's advanced number theory, but just take a quick look at the quantum Fourier transform. So if we have, so here we have 16 states, so that we can represent that with just 4 qubits. And so we have 16 values here, and each one has a little bit different phase angle. You can see actually the phase angle is progressing, and that represents a frequency. So if we take the Fourier transform of that, we end up with a little spike here as the answer. And this is the circuit. I don't even understand it fully myself, but that's how you do a quantum Fourier transform. Taking a little deeper look at Grover's algorithm for searching, we've seen this amplitude amplification. You may be wondering, why don't we just do one iteration and see which one is the tallest? Can we just do that? Well, we want to be certain of our answer. So if the amplitude is not all the way strong at 0 or 1 on our correct answer, we're just going to get a random value. And Grover's algorithm actually stores its results in terms of phases. And so each iteration of the Grover iteration, what it's actually doing is it's yanking that phase around so that it becomes an amplitude, and that amplitude can be read out. And this is the algorithm, or the circuit. So they ironically call this an oracle. This is essentially a callback, right? We don't actually have functions in a quantum circuit. It's a circuit. So they call it an oracle. This determines what we're searching for. It returns a 1 for the value that we're searching for. And then this is the circuit for one iteration of the Grover iteration, or amplitude amplification. Now there's a more recent algorithm from 2009. This solves a system of linear equations, and it also uses the quantum Fourier transform in the background. But a consequence of that is that it leaves the answer in terms stored in terms of phases, which are difficult to read out. So this algorithm is actually more useful if you plan to use the output in a downstream circuit, such as for machine learning. So how many qubits do we have these days? Well, let's go take a look. So, the first quantum computer way back in 1998 had 2 qubits. IBM Quantum Experience with 5 qubits actually came out in 2016. And then an important date in the history of quantum computing is 2019, when quantum advantage was reached. This used to be known as quantum supremacy until the events of 2020, but what it means is that a quantum computer solved a problem that would take way too long on a classical computer. And in this case, it was a single chip containing 54 qubits, of which 53 were used and solved a problem, not a useful problem, but a problem in 200 seconds that would have taken a classical computer 10,000 years to solve. And so that was 2019. By 2023, IBM hopes to have 1,000 qubits. And again, this is in the lab. Out in production on the cloud, it's a fewer number of qubits that are commercially available. I believe it's 5 qubits are free, and then you have to pay a little more if you want 17 or 20 qubits. If we assume that the number of qubits is going to double every year, which is an aggressive assumption considering Moore's law was 18 or 24 months for every doubling. But if they double every year, then in 14 years we'll approach the number of qubits expected or to be needed to crack RSA. And RSA encryption, that's what it's used in HTTPS. So in 2037, you won't be able to type your credit card number into Amazon anymore. Now you've probably heard of D-Wave. They have much higher number of qubits, but the D-Wave computers are not general purpose quantum computers. They're called adiabatic quantum computers. They're basically hardwired to one specific algorithm called quantum annealing, which is an optimization algorithm. So it's an important algorithm, but you couldn't run, for example, Shor's factorization algorithm on a D-Wave to crack RSA. So how much information, from an information theoretic standpoint, how many classical bits could correspond to what you can put into one qubit? Well, in terms of what you can measure, there's only one bit in a qubit, right? It's the 0 state or the 1 state. Now, when you get into quantum communication using entangled photons over fiber optic cables, those protocols typically encode 2 bits within 1 qubit, and they give it this hyperbolic name, superdense coding. But I think it's reasonable. You could come up with 10 internal states here that would be distinguishable even in the presence of some noise. One guy is proposing, essentially 3.3 bits per qubit. He calls them qudits, kind of a base 10 approach to quantum computing. But I think, it's fair to say we could have 4 bits, 16 distinguishable positions on this block sphere. So if we go with the number 4 bits, and we're talking about the 5 qubits on IBM Quantum Experience, there's 2 to the 5th states, 32 states. Each state has 4 bits, so that's 128 bits, or 16 bytes. So 16 bytes. I'm going to take a digression into what I call toys of my youth. So this isn't a toy. This is an Altair. This is the first computer programming class I took in 1977. The instructor had built this computer from a kit because you couldn't walk into a store and buy an assembled computer. You had to solder one together yourself, which he did and taught us how to program. But then my parents weren't able to afford a computer for me until 1981. In the interim, I had to satisfy myself with these toys. Well, actually, the TI-59 is not a toy. It's a professional thing, but most people would not call it a computer. But anyway, these 2 toys, they each had 64 bytes. And that's kind of comparable to the 16 bytes, especially when you consider that these 64 bytes have to hold both code and data. And in a quantum computer, remember, our code is sitting in a Jupyter notebook and controlling microwave signal generators, and the qubits are really only for data. So it's quite comparable. So we could call the 2016 IBM Quantum Experience with 5 qubits, we could call that a toy, and that was 5 years ago. So if we're trying to draw a timeline analogy here, 5 years after 1978 is 1983. So you could say that we are in the 1983 of quantum computing right now. So, I've been hinting at, I didn't like the 0 and 1 nomenclature, and well, here's why. And this is not strictly what's going on, but it's more of like a physics analogy. But, there are higher level harmonics that a qubit can hold, basically higher frequencies. And, why don't we use those higher frequencies? Well, imagine you're pulling up to a stoplight, the car next to you has heavily tinted windows, and what do you hear? All you hear is thump, thump, thump. All the higher frequencies are filtered out. It's harder to deal with these higher frequencies. There is one line of research out there looking at Q-trits, where they use the 0, 1, and 2 states simultaneously. But again, these are going to be subject to noise, and noise is presently the bane of quantum computing's existence. Okay, now we're going to take a look at some advanced and miscellaneous topics. So first at the hardware, and there are multiple different technologies that can be used to realize quantum measurements. So there are photons, for example, but these are used mostly just for communication and not computation. And there are 2 reasons for that. One is that photons travel at the speed of light all the time, which makes them kind of squirrely. And what's worse is that when one photon collides into another photon, they just pass right through each other, which makes constructing gates difficult. So this is an actual image. I wouldn't call it a photograph, but it's an image of individual ions, and these are trapped in an electromagnetic field. You can kind of see the limitation here. It's all just in one dimension. They would, to make this scale out, they would have to figure out how to create an electromagnetic field to contain a 2-dimensional, even better 3-dimensional matrix of these trapped ions. NMR, nuclear magnetic resonance, is actually the technology that was used in the first quantum computer in 1998. This is a liquid version. They've moved on to solid state versions, but basically in an NMR, when you want to read a quantum state, you're basically doing an MRI on your NMR or on your substance. Nitrogen vacancy is a crystal where one atom has been removed and replaced with a nitrogen atom, and another atom has been removed and just left as a vacancy, and that's all I know about that. I don't know how the qubit values are set and read. But the reason IBM and most other vendors have chosen superconducting is because of you don't actually have to go down to the atomic level. What they do is they use a Josephine junction, which is a 1 nanometer thick insulator separating 2 superconductors. And this realizes the quantum effect. What I mean by quantum effect are these discrete type measurements, 0 or 1. So they don't have to go down to the molecular level. I mean, it's close, but 1 nanometer is larger than the width of this fin on this transistor. Conventional classical transistor, a FinFET transistor, is only 0.6 nanometers wide. So that means they can use conventional silicon chip manufacturing to engineer these and manufacture quantum chips. So here's that 0.5 Kelvin again. You may be wondering how they get down that low, because helium liquefies at 4 degrees Kelvin, which is the typical very low temperature that can be reached. So they pull this trick where they use a combination of helium-3 and helium-4. So helium-4, that's the natural isotope, right? Two neutrons, two protons. Helium-3 is much more rare, very rare. But I guess what happens is the helium-3 and the helium-4 don't really mix. It's kind of like oil and water, and they somehow accomplish 0.5 Kelvin out of that. And because helium-3 is so rare and this is so complex, these dilution chambers cost millions of dollars. So they're trying to come up with 1.5 Kelvin instead of 0.5 Kelvin superconducting qubits, in which case they could have a chiller that's costs only thousands of dollars instead of millions of dollars. Again, to flip qubits around and change their state, you're pumping in microwaves. And even that's not really a settled science. I mean, there are different technologies of microwaves that they're playing around with. So I've kind of been glossing over this idea of entanglement, that you can entangle any qubit with any other, but real life qubits have an actual topology to them. So if you need to entangle this top qubit with this middle qubit, what happens is your Qiskit Python library behind the scenes is going to do some compiler optimizations and switch qubits around, maybe even on the fly, to get things to entangle with each other. Now this is not some Excel chart. This is an actual output out of Jupyter Notebook running Qiskit. You could assume here we just have a one gate circuit that's an H gate that entangles into a 50-50 superposition, in which case you would expect to read 0 50% of the time and read 1 50% of the time. And so if you run that circuit 1,000 times, you would expect 500 and 500, but actually in this case it was 501 and 499. And again, that's because of noise. So when you run your circuit, Qiskit gives you three different modes. You can run an ideal simulator, in which case you would get 500 and 500 every time, or you can run a simulator with simulated noise, or you can run it on actual hardware. So I think on the free tier on IBM Quantum Experience, you get a certain number of runs that you can run for free, and after that it costs money. So, we've been talking about noise. This stuff is not 100% reliable, but you can quantify the unreliableness. So both the amplitude and the phase are unreliable, and the decay chart for amplitude is called the T1 decoherence, and the phase decay is called T2 decoherence. And, that was for the qubits. Now, the gates themselves have their own problems, where it's called fidelity. Thankfully, gates today are at the 4 nines, way down here. And that's good, because if you have 100 gates in a row in sequence, your accuracy is going to drop from 4 nines down to 2 nines. Now, imagine if each individual gate only had 2 nines, like in the 2014-2015 time frame, and then you run it through 100 gates, you're down now to 37% accuracy, which really isn't usable. So we're just now coming into usability. Now these different hardware realizations of quantum effects have quite different performance characteristics. This is hard to read, but this is a logarithmic scale where each tick is another factor of 1,000, 10 to the third. So you can see that superconducting is 1,000 or 1,000,000 times as fast as other technologies, and in terms of gate time, which is you could live with a slower gate time if your decoherence time was also really long, but superconductors, qubits really strike the great balance. Not only are they fast, but they're fast relative to their decoherence. So the decoherence time on superconducting is actually pretty short, but it's much longer than the gate time. So this fantasy world, long term, we want to have the quantum internet. But in the short to medium term, what we're really interested in is just using quantum communication channels to transmit encryption keys, classical encryption keys for classical computers running classical encryption algorithms. And they've gotten pretty good at it. They can transmit entangled photons down a fiber optic cable, 500 kilometers so far. Now there's this term called teleportation. It's kind of a groaner of a term because nothing actually gets teleported in Star Trek, like in Star Trek. What you're doing is you're teleporting the state. I could use the word copying state from Alice to Bob, but remember, if we want to copy the state, we have to destroy Alice's state. So I guess that's why it's called teleportation. There are a couple of things that you have to do, though, to realize this. First, you have to give Alice and Bob a pair of entangled qubits. Alice gets one, Bob gets the other. And you still have to maintain a classical channel to have a full protocol, like for confirmation. It's still secure on the quantum channel, but you still need that side channel to realize the full protocol. And the first particular protocol is called BB84, and as you might guess, this was invented in 1984, which is a little surprising, right? This is 14 years before the first quantum computer. But it involves this complex flowchart that I'm not going to go through. But the basic idea is that Alice gets to decide at random whether she's going to encode using vertical polarization of her photons or diagonal polarization. And Bob has to guess, and if Bob guesses the same, then he gets a valid read. If he guesses incorrectly, he has to throw that data away. And this is coordinated through an open, non-encrypted classical communication channel that Eve can eavesdrop on. And so if Eve is trying to be a person in the middle, Eve has to guess what the polarization is, and hopefully guesses correctly and then re-encodes that photon, because once Eve reads it, that photon is destroyed. Re-encode a new photon and send it off to Bob, and hopefully from Eve's point of view, getting the correct polarization so Bob doesn't know the better. So Eve has a 50-50 chance on guessing that correctly. But then if you force Eve to do this over a number of qubits, like say 10 qubits, then Eve only has a 1 in 1,000 chance of guessing this correctly, or 20 qubits, 1 in a million chance. So you choose your probability, and then once your link is established, then you can transmit a number of qubits, enough for your encryption key, your conventional classical encryption key. So you might be wondering, okay, with all these errors floating around, can we apply error correction algorithms from the classical world? And the answer is maybe, kind of. It's really hard, right? The no cloning theorem just makes it difficult, makes everything difficult. And then remember, we're not just correcting zeros and ones here. These are continuous analog values in both the amplitude dimension and the phase dimension. And so at this point in time, it's actually better to just forget error correction and focus on making your qubits more noise resistant. I mean, this is kind of like the most basic form of error correction here. It's triple redundancy. You convert your 0 into a 3-qubit entanglement of 3 zeros and 1 into 3 ones. But you need 2 extra qubits just for the encoding, and then another 2 qubits to decode, so that's a 5-to-1 ratio. Well, our IBM Quantum Experience only has 5 qubits to begin with, so you can really burn up your qubits, and they're scarce these days. Maybe eventually they'll get there. Oh, and this circuit only corrects to 0 or 1. It's not going to correct back to your finely tuned theta and phi angles. All right, so what I've been talking about in this presentation is basically the quantum circuit model of quantum computing. D-Wave uses that other model of computing, which only performs quantum annealing. And another model of computing is hybrid, a hybrid between quantum and classical computers. And the algorithm that exhibits that the best is the quantum approximation optimization algorithm, QAOA. And it's basically a ping-ponging between quantum computing and classical. Quantum does one step of the optimization, hands it off to a classical computer. The classical computer computes what the next iteration should be, basically like stochastic gradient descent, and it just goes back and forth, converging on the solution. So let's look at a little bit of science history here. So all the way back in 1877 was when Boltzmann was proposing integer or quantum effects at the molecular level. So what is it, 144 years later, quantum computing is becoming ripe. All right, and then Planck formalized what Boltzmann was conjecturing in terms of the Planck constant. And then quantum mechanics really came into its own all in the 1920s. Now, in terms of politics, 2 years ago, the National Quantum Initiative Act was passed. This provides funding for quantum research. So, quantum became a national security interest 2 years ago. Now, I don't pretend to understand wave-particle duality. I don't know that many people do, but I want to call your attention over here to the Stern-Gerlach experiment. So this is shooting out silver ions through these magnets. So an individual silver ion is going to land either here or here, nothing in between. So this is basically what doesn't happen. This number 4 here is what you might expect in the classical world, but down at the quantum world, it's very discrete. It's either here or here. Now, the other place where we see this very discrete behavior is, within individual atoms. Electron shells are very discrete because they're discrete multiples of a frequency in Planck's constant. So just to repeat that mantra of quantum mechanics: superposition, entanglement, interference. Superposition is why a qubit can have 0 and 1 simultaneously. Entanglement is why we can represent 2 to the n values with n qubits. And interference is what allows us to have phase angles within each qubit, individual qubits, and then multiple qubits together allows us to do things like the quantum Fourier transform, where we have phase angles just all over the place. In terms of books, I mean, there's like only 8 or 10 books. These are my 2 favorite. Even though this one came out in 2007, this is actually a very large format book and very thin with a lot of pretty pictures. Very readable book. This is also very readable, and remember, this is the book that has its own unique visualization of qubit states. But I really like this book because the authors just have this deep intuitive understanding of everything quantum. And this book is available for free to Oracle employees through O'Reilly Safari, and this is the URL for it. And that is it.